Welcome to Math with Professor V. In this video, we're going to learn all about triple integrals and cylindrical coordinates. First, let's just go over the basics of the cylindrical coordinate system. Now, the cylindrical coordinate system is a three-dimensional coordinate system. And so we represent a point P in 3 space as an ordered triple whose coordinates are given by r, theta, z. So r and theta are the same as from polar coordinates. Polar coordinates are in 2D, cylindrical just bumps it up to 3D. And it's the projection of P onto the XY plane. Z is the directed distance from the XY plane to P. So when you're converting back and forth, you use the same conversion that you would to go from rectangular to polar, namely X is r cosine theta, Y is r sine theta, and then Z is equal to Z. We don't touch that. Similarly, x squared plus y squared is r squared, and tangent of theta is equal to y over x. Let me just draw for you an arbitrary point. We'll just put it in the first octant to keep things relaxing so you can get a feel for this new coordinate system. So there's our x, y, and z axes, okay? And say I have some point P here, okay? And normally you would represent it that it's at x, y, z, but now we're going to represent it in cylindrical coordinates r, theta, z. So how do we measure it out? Well, first we have to figure out what the projection is in the xy plane. So this distance here, that would be r. That's our normal polar coordinate way of measuring to a point. And here's theta, measured counterclockwise from the positive x-axis. And then this distance here, z, is the same, whether you're in cylindrical or rectangular. This distance here is r across the top. Let me straighten it out. Good? Okay, so you'll see we're going to just familiarize ourselves with this cylindrical coordinate system, and then we'll evaluate integrals using it. That would be really nasty to do in rectangular, but are much nicer when we're in cylindrical. Just like, didn't you go over double integrals in polar and it was better for a lot of circular regions? Same thing here. Okay, plot the point whose cylindrical coordinates are given, then find the rectangular coordinates of the point. So we have 4 pi over 3, negative 2. So this is r, this is theta, this is z, okay? So let's go ahead, let's plot it. So we're gonna sweep out an angle, pi over 3, counterclockwise from the positive x-axis, extend 4 units from the origin, and then, project downward in the z direction 2 units. Okay, so just be precise about your labeling and all is well. I'll say up to here, swooping out, that's pi over 3. I'll say this is length 4, because I said so. And then we'll project 2 units downward in the z direction since the z coordinate is negative 2. So that distance I need to tack onto here. So that's where the point's going to be. That's 4 pi over 3, negative 2. Okay, very good. Then find the rectangular coordinates of the point. Okay, so x is going to be r cosine theta, so 4 cosine pi over 3. So what would that give us? That's going to be 4 times cosine of pi over 3 is a half, which is 2. Y is 4 sine pi over 3, so that's 4 times rad 3 over 2, so that's 2 rad 3, and then z is the same. Z is just negative 2. So in rectangular coordinates, this is 2 rad 3, negative 2. Voila. How was that? Okay, relaxing. Let's look at another example. Change from rectangular to cylindrical coordinates. So we don't need to graph, we just need to convert. So this is currently in x, y, z, rectangular. Okay, so first we're going to find r. Remember, r squared is equal to x squared plus y squared. So that's going to equal negative 1 squared plus 1 squared, which is 2. So we'll just by convention, we always take r to be positive. So r is going to be rad 2. Then I need to figure out what theta is. So tangent of theta is y over x, which is going to be 1 over negative 1. So now you have to be a little careful and think to yourself, okay, when does tangent equal negative 1? But notice x has to be negative and y has to be positive. You can just think that you're in the xy plane. This would correspond to being in quadrant 2. Quadrant 2. Since x is negative and y is positive. So I know I'm going to have a pi over 4 reference angle, but being in quadrant 2 means that theta is equal to, that's right, 3 pi over 4. And z doesn't change. So I've got r, I've got theta, and then we keep z the same. So in cylindrical, this is going to be rad 2, 3 pi over 4, and positive 1. Okay? Good. Why don't you guys try the next one? Oh, this square root sign is too long. It's too excited. It should only apply to the second coordinate. Please forgive me. Okay, here we go. So currently we are in rectangular. This is x, this is y, this is z. Let's get r. So r squared equals negative 2 squared plus 2 rad 3 squared. So that's going to be 4 plus 12, which is 16. So r is 4. And then tangent of theta is 2 rad 3 over negative 2, which is negative rad 3. Again, you could think we're in basically quadrant 2. Just imagine the xy plane. You don't have to imagine in 3 space. So in quadrant 2, we're going to have a reference angle of pi over 3. So my theta is 2 pi over 3. Okay, so then in cylindrical coordinates, this is going to be 4, 2 pi over 3, and then z doesn't change. Z is still 3. How are we doing? Okay, very good. Write the equations in cylindrical coordinates. You're going to do this often when you're setting up your integrals. So we have x squared minus x plus y squared plus z squared equals 1. Remember, you can only involve the variables r, theta, and z when you're in cylindrical. So as soon as I see, ooh, I got x squared plus y squared, I'm going to replace those with r squared. Then I have minus x. X I'll replace with r cosine theta plus z squared is 1. And then typically if you can solve for z, that's the way you want to go. So I'm just going to isolate z squared and leave this as 1 minus r squared plus r cosine theta. And that's pretty much as cleaned up as we can get. Good? Okay, next one, z equals x squared minus y squared. So z is already isolated. I'm just going to replace x with r cosine theta. That'll get squared. And then y with r sine theta. That's squared as well. So this is r squared cos squared theta minus r squared sine squared theta. Now I can factor out an r squared. And then we have cos squared theta minus sine squared theta. And yep, that's our double angle identity. That's cosine 2 theta. Okay, so I'd say this is as cleaned up as it's going to get. Z equals r squared cosine 2 theta. Good. Okay, very nice. Next example, sketch the solid described by the given inequalities. So we've got r squared is less than or equal to z is less than or equal to 8 minus r squared. So let's look at this lower bound. Z is always greater than or equal to r squared. Well, if z equals r squared, what is that? Maybe you need to write it in rectangular to recognize it. Z equals x squared plus y squared. That's a paraboloid. The vertex of it is at the origin, right? And it's opening upward. What about z equals 8 minus r squared, the upper bound? So z equals 8 minus r squared. That's the same as 8 minus x squared minus y squared. That's a paraboloid opening downward. Very good. And it's been shifted up 8 units, yes? Okay. Now let's figure out where these intersect. That's important. We're going to sketch this solid, so we need to know precisely where r squared is equal to 8 minus r squared. So that means 2r squared is 8, r squared is 4. So that happens when r is 2. And if r is 2, I can see here, that implies z is equal to 4. Okay, so that's when these two paraboloids are going to intersect at z equals 4 at a circle of radius 2. I think we're ready to put a nice, gorgeous picture together. Do you feel ready? We remember what paraboloids look like. One's opening up, one's opening down, and they're going to intersect when z is 4. But let me go all the way up to 8, right? Because one of them has been shifted up 8 units, 5, 6, 7, 8. I'm not counting you down to a dance routine, but I mean, we could do that later. Okay, and then the radius is 2, where they intersect. Okay, here we go. So we have this paraboloid up here, shifted up 8 units. It's going to intersect with the other paraboloid that's opening downward when z is 4 at a circle of radius 2. So I'm trying to eyeball best I can. Very good. Then I have the paraboloid opening upward. It's going to intersect at the same place. So this is z equals r squared. And this is z equals 8 minus r squared. Hopefully you can see that intersection occurs at a circle of radius 2. So z is everything between and on these paraboloids. So you can just shade, it looks like an egg, yes? Yes, everything on and between. Beautiful. Okay, very good. Sketch, that's all we need to do. You don't need to write too many words. All right, let's move on. Now it'll get good. Use cylindrical coordinates to evaluate this triple integral where E is the region that lies inside the cylinder, x squared plus y squared equals 16, and between the planes, z equals -5 and z equals 4. Now, I tell my students this all the time. The textbook will not say sketch the solid E or sketch the base region, but you need to do it. I will state that on the exam, and you just shouldn't even attempt to set these up without a nice graph of what's going on. Now, I just want to, for the sake of making sure everyone's on the same page, go over, like, what does this integral exactly represent, right? So I want you to think back when you were in Calc 1 and you just had definite integral from a to b of f of x dx. What did that represent? That definite integral represented the area underneath the curve of f of x from a to b. So this gave you a two-dimensional quantity. This gave us area. Why was it a two-dimensional quantity? Because we had one integral sign that was summing up all of these function heights. So that gives you 2 dimensions. Now, what have we started to do? We started to look at double integrals. Now, when we have double integrals with, limits of integration, say a, b, c, d, double integrals, and then you also integrate a function, dA, this gives us a 3D quantity. This gives us volume, yes? And the way you can think about it is 1 dimension, 2 dimensions, 3 dimensions, okay? Now, you've also worked with double integrals that just gave you area. That's because you had limits of integration and you had no function. So in that case, there's no f of x, there's just dA. And this gives you a 2D quantity. This gives you the area of the region enclosed by whatever is described by those limits of integration. So again, count it up this way. 1 dimension, 2 dimension, no function, so it's 2D, it's area. Similarly, okay, say you have a triple integral and then just a dv, no function. This gives you a 3D quantity. This gives you a volume. Say you have a triple integral, it's over E, that's what we call it here, f dv, which is what we're being asked to do here. Here's my function, dv. What dimension, quantity does this represent? 1, 2, 3, 4. You might say, Professor V, what is 4D? What is that? It depends on what f is, okay? So whatever, we're not going to describe it because we live in a 3-dimensional world. But just keep in mind or keep track of what these integrals represent, because sometimes you'll be asked to find volumes and you'll need a triple integral or you'll need a double integral. Sometimes you'll be finding area, you might use a double integral. So just pay attention to what's going on, and you could just count it up. Each integral is a dimension, and then if you add in a function that you're summing up, that adds one more, all right? So for number 5, we're just evaluating this triple integral with a function. So it's a 4-dimensional quantity. Never mind what it represents right now. They didn't give us any context, so we'll just leave it as is. Now, my limits of integration are determined by E. E is the region that lies inside the cylinder, x squared plus y squared equals 16, and then between the planes, z equals -5 and z equals 4. Okay, so here's what's going on. Z equals -5, z equals 4. We know what that looks like. Those will just be 2 planes parallel to the xy plane. Okay, and then we've got the cylinder, x squared plus y squared equals 16. 1, 2, so radius is 4. 1, 2, 3, 4. Okay, so we've got, this is the base, x squared plus y squared equals 16. Then we're going to go up to z equals 4, and then down to z equals -5. Boom. Oh, that one's, hold on. All right. So this is E. This is what we're integrating over. We're going to set it up in the cylindrical coordinate system. So that means I need to represent my solid E in terms of R, theta, and Z. Okay? So R and theta, all you need to do is imagine the projection in the XY plane. And in the XY plane, E is just a circle. It's a circle, radius 4. I have that from this equation right here. So let's draw that out as well. So pretend you're basically standing on top of the solid. You're up here looking down. Okay, so we've got a circle, radius 4. And now you guys need to determine what would the limits of integration be. Too big. What would the limits of integration be in terms of R and theta to represent this entire circle? Okay, well, we're going all the way around. So theta should vary from 0 to 2 pi. And R, to figure that out, always start at the origin and then draw a ray going outward. Where it starts is your lower limit. Where it exits the region is the upper limit. So it's going from R equals 0 all the way to R equals 4 in any direction, right? It's always 0 to 4, 0 to 4. The radius is the same length everywhere. Okay, good. So I think that part's taken care of, R and theta. Now we need to look at the 3D graph and figure out what are our limits for Z going to be. Well, just imagine now in the positive Z direction, an arrow going straight through your solid. Where it enters the solid is the lower limit for Z. Where it exits the solid is the upper limit for Z. So it's going from Z equals -5 all the way to +4. Okay, very good. Only other thing we need to do is change the integrand so it's in terms of cylindrical coordinates as well. So square root of x squared plus y squared in cylindrical coordinates, that's square root of r squared, which is just going to be r. We don't need to put absolute value. So here we go. We have now integral 0 to 2 pi, 0 to 4, -5 to 4, square root of r squared, which is r, and then dv in cylindrical coordinates is basically polar, but then add on dz. So it's r, dz, dr, d theta. This extra r comes from the dr, d theta when we convert to polar. And I showed in another video lecture why we have that extra r, so go back and watch it if you want. Okay, from here we can just evaluate the integral. Not too wild. I don't see any thetas and all my limits are constants. So I can just slap a 2 pi on here. Yep, I sure can. And then I have integral 0 to 4, -5 to 4, r squared, dz, dr. Again, I don't see any z's, so if I integrate, I'll get a z. Upper limit minus lower limit, I can just jump to that. 4 minus -5 is 9. Yeah, so we've got 2 pi times 9, integral 0 to 4 r squared dr. And then that's going to be 18 pi times 1/3 r cubed, evaluated from 0 to 4. 18 pi over 3 is 6 pi times 4 cubed minus 0 cubed. And this will give us 384 pi. Very good. Beautiful. Okay, that one wasn't too crazy. It was just a cylinder. Let's go ahead and look at another example. So evaluate the triple integral of x squared dv, where E is the solid that lies within the cylinder, x squared plus y squared equals 1, above the plane z equals 0, and below the cone z squared equals 4x squared plus 4y squared. Okay, so before we start drawing a picture, we need to figure out the intersection of these surfaces. Namely, I need to figure out where the cylinder and the cone intersect. The plane z equals 0, that's just the xy plane. I got that, you know. So let's see, x squared plus y squared equals 1. So I could say z squared equals 4 times x squared plus y squared, and I know from the cylinder this is equal to 1. So they intersect when z squared is 4, which would be equivalent to z equaling plus or minus 2. But since we are above the plane z equals 0, then I know we're not dealing with any negative values. It's where z equals positive 2 only. Okay, that's where they're going to intersect. So we're really only working with a half cone, the upper half of the cone, and it's trapped inside this cylinder, x squared plus y squared equals 1, and they intersect when z is 2. Okay, I think we got it. So they're going to intersect when z is 2. We've got a cone, like so, and then it's trapped inside this cylinder. That's where they intersect. Okay, things are scaled somewhat. This is 1, right? Because the cylinder's radius is 1. Boom. Okay, so E is the solid that lies within the cylinder, above the plane z equals 0, and below the cone. Okay. So if E is within the cylinder, it's above z equals 0, and it's below this cone. It's all of this outer portion here. Okay, so basically imagine you had a cylinder and someone came and scooped a cone out of it. This is all hollow. Okay. Okay, now let's figure out what the limits of integration would be to describe this solid E in the cylindrical coordinate system. So first I'm going to draw just the xy plane. So we want to imagine what would be the projection of this solid E in the xy plane. So again, if you're standing here looking down at the solid, all you would see is a circle, radius 1. Yes? Okay, so here's a circle, radius 1, and the entire thing is filled in. The entire thing is part of the integration region. So very similar to the last problem. Theta will vary from 0 to 2 pi, and r, draw your little ray if you need it, it'll go from 0 to 1. Perfect. Now we have to figure out what the limits of integration are for z. In that case, you need to look back at the 3D picture. Again, draw an arrow upward in the positive z direction. I always tell my class, just imagine you're shooting a bullet through the solid. Where it enters is the lower limit, where it exits is the upper limit. So it enters at z equals 0, the xy plane, and then it exits at the cone. What's the equation of the cone? Z squared equals 4x squared plus 4y squared. We got to put that into cylindrical. So that's z squared equals 4r squared, which is z equals 2r. So the limits for z are from 0 to 2r. All right, good. Now let's set it up. So we'll have integral 0 to 2 pi. Theta is on the outside 99% of the time. r goes from 0 to 1, and z goes from 0 to 2r. And then my integrand is x squared. So in cylindrical, that's r cosine theta squared. And then I have dv, which is r dz dr d theta. Okay, now scanning through, I have thetas, I have r's, so no shortcuts allowed this time. And the limits are not all constants. So here we go, one at a time. This will be integral 0 to 2 pi, 0 to 1. Now, I don't see any z's, so if I integrate with respect to z, then I'll just pick up a z and evaluate it from 2r to 0, so I'll just pick up another 2r as well. So I've got 2r, and then this is r squared cosine squared theta, and then another r dr d theta. Good, good, good. Okay, now let's see here. Can we take any shortcuts? We can split it into two integrals of a single variable, right? Because everything's a product of r's and thetas, and all my limits are constants. So I can go 0 to 2 pi, and I'll just have cosine squared theta d theta. And then I can also evaluate from 0 to 1, how many r's do I have? 1, 2, 3, 4. So 2r to the fourth dr. So here we go. How do you integrate cosine squared theta? You replace it with 1/2 times 1 plus cosine 2 theta d theta. This will get evaluated from 0 to 2 pi. And then 2r to the fourth antiderivative would be 2/5 r to the fifth evaluated from 0 to 1. So this is going to give me 1/2 times, I'll have theta plus 1/2 sine 2 theta evaluated from 0 to 2 pi. And then this is just 2/5. Beautiful. So 1/2, 2/5, those will cancel. I'll just get 1/5. And then we have 2 pi plus 1/2 times sine of 4 pi 0 minus a bunch of zeros. So this just gives me 2 pi over 5. Hopefully evaluating them is not the hard part, huh? Okay, good, good. Let's look at another. Find the volume of the solid that is enclosed by the cone, z equals rad x squared plus y squared, and the sphere, x squared plus y squared plus z squared equals 2. So this time, if we're asked to find a volume, we're just going to set up triple integral over e, no function, dv, all right? So we've got a cone and a sphere, and we have to figure out, of course, where their intersection is before we even think about graphing. So intersection is going to be where, notice here I have a z squared in this equation, so let me square the cone equation. Z squared equals x squared plus y squared. Then I'll just sub that in here. So if z squared is x squared plus y squared, I've got x squared plus y squared plus another x squared plus y squared equals 2. So then that's 2x squared plus 2y squared is 2. So they intersect in a circle, radius 1. Very good. X squared plus y squared equals 1. So this is equivalent as well as saying they intersect where z is equal to 1. Why do I say that? Because look at the cone's equation. It's rad x squared plus y squared. So again, x squared plus y squared equals 1 and z equals 1 is where the cone and this sphere are going to intersect. Okay, so let's see if we can graph what's going on. The cone, it's just the upper half of the cone because you see we only have the positive radical. And then the sphere, well, we're just going to be above the xy plane since we're only dealing with the upper half of the cone anyways. Now, the radius of the sphere is rad 2, is it not? Yes, it is. Okay, so here's 1. Here's 2, and rad 2 is about 1.4. So the sphere is going to open downward because we're just dealing with that top half. 1, 2. I'll say here's the sphere. Coming in hot. Here's the sphere. Radius rad 2. And then I've got this cone. It's opening upward. It's going to intersect the sphere. Boom. It intersects the sphere. It makes a circle, radius 1. Hopefully you can see. Yep, that's radius 1. And that intersection happens at z equals 1. Okay, so what solid is enclosed by this cone and the sphere? So this cone is opening upward, and this sphere, you can think of it, it's kind of like opening downward. We're really enclosing this cute little snow cone. You see it? You see the snow cone? Enclosed by the sphere and the cone. Okay, so let's go ahead. Let's determine how to set up an integral to find the volume. We're going to work in cylindrical coordinates. Imagine you're up here looking down. All you would see is a circle. You would see this circle, x squared plus y squared equals 1. Can you figure out what the limits of integration should be? Just think you're only in polar, and then we're just going to add z after, okay? So limits of integration for a circle, radius 1, and we want the whole circle, don't we? Yes, the whole circle, all the way around and around. Okay, so the radius is 1, theta is going to go from 0 to 2 pi, r from 0 to 1. Okay, now to get the limits for z, you have to look at the 3D picture. Draw an arrow through the solid in the positive z direction. Where it enters is the lower limit of integration. Where it exits is the upper limit of integration. Okay, you can pretend you're shooting a bullet through your snow cone. It enters at the cone, exits at the sphere. Enters at the cone, so z enters when z equals rad x squared plus y squared, which is z equals r, so that's my lower limit. It exits at the sphere, which is z equals, ooh, we gotta find it. I don't have that. Okay, so z squared equals 2 minus x squared minus y squared. So z equals plus or minus square root, but I'm only using the positive because we're using the upper half of the sphere, 2 minus r squared. So that's my upper limit. Square root 2 minus r squared. Are we all right? So you're shooting a bullet through your snow cone. Just draw an arrow going through. Where it enters, that's the cone. Z equals r, that's my lower limit. Where it exits, that's the sphere, that's my upper limit, rad 2 minus r squared. Okay, here we go. So the volume is going to be integral from 0 to 2 pi, 0 to 1, r to rad 2 minus r squared. No function because we're finding a volume, right? Sorry, that v looked so ugly. And then we'll have r dz, dr, d theta. Now I see no thetas anywhere, so I can just slap a 2 pi on here. Then we have 0 to 1. If I integrate with respect to z, I'm just going to pick up a z, upper limit minus lower limit. So let's just cut to the chase. We'll have r times square root 2 minus r squared minus r squared dr. Good? Okay, now for this first term, you would need to do a u sub, but we can just mentally walk through it. That way we don't have to split this into two integrals. Keep the 2 pi out there, okay? If you were to u sub it, you'd let u equal 2 minus r squared. Du would be negative 2r dr. I don't have a negative 2, so when I integrate, I'll pick up a negative 1/2. Then 2 minus r squared is currently to the 1/2 power. If I integrate, I'll add 1 to the exponent. It'll be to the 3/2. And then I have to divide by that new exponent. So that whole first term is taken care of. And then I have minus 1/3 r cubed. This is evaluated from 0 to 1. Look at how effortless. So we've got 2 pi times negative 1/3, 2 minus r squared to the 3/2 minus 1/3 r cubed, 0 to 1. And then this is 2 pi times negative 1/3 times 1 minus 1/3 minus negative 1/3 times 2 minus 0 or plus 0, but whatever. Okay, and then this will clean up to 4 pi over 3 times rad 2 minus 1. Fabulous. Very good. Box that with pride. That was a job well done. All right. Last one of my favorites. Evaluate the integral by changing to cylindrical coordinates. So we have this triple integral, and the way to switch it to cylindrical is to graph the integration region. Okay, So here we go. We can actually just do a 2D graph. Notice my limits for y, those go from -2 to 2, and x goes from negative rad 4 minus y squared to positive rad 4 minus y squared. Well, this is just describing the left and right halves of a circle, radius 2, centered at the origin, and y is going all the way from -2 to 2. So what's happening is in the xy plane, we have the entire circle, right? All 4 quadrants, radius 2. Let me move this so it's beautifully centered. Yes, so this left half, let me highlight for you. This left half is negative square root 4 minus y squared. And then this right half is positive rad 4 minus y squared. And then y goes all the way from -2 to 2. So we really just have this entire circle. Could we describe that with polar coordinates more easily? Absolutely. Theta would go all the way around, so 0 to 2 pi. And r would go from, very good, 0 to 2. The radius is 2. Let me add that in there. That was bad of me. Okay. Now, z is not so difficult because you can imagine this is a cone and that's a plane. I'll graph it for you if you want, but you could just switch it very easily because z is still z, right? You just have to change the equation to be in the cylindrical coordinate system. So if z is rad x squared plus y squared, that's the same as rad r squared. So that's just going to be r. So z goes from r to 2. Can you imagine what this is going to look like? So the cone bounds the solid below, and then the plane z equals 2 bounds it above. X, y, z. 1, 2, yes? Here, the cone bounds it below, and it's got a flat top. The plane z equals 2 bounds it above. Z equals 2, and then it's bounded below by the cone, and that's why when you look down on it in the xy plane, all you see is a circle, radius 2 all the way around. Okay, beautiful. I think we're ready to set it up. So this integral is going to go 0 to 2 pi, r is 0 to 2, z would go r to 2, and then be careful. So xz, x in cylindrical is r cosine theta, and z is z. And then you have r dz, dr, d theta. Okay. Now, what does this integral represent? It's not a volume, right? It's some 4-dimensional quantity. Okay. I'll let you work through it. It comes out to 0. I know. Somewhat unsatisfying. But anyways, that's that. I hope you found the video helpful. If you need more help with triple integrals, cylindrical coordinates, spherical coordinates, then check out the rest of the video lectures on this playlist, Calculus 3 video lectures. I have so many. And I also have videos where I work through old exams that I've given in previous semesters just to give you an idea of what kind of questions maybe you'll encounter and just different tools to help you get prepped. So don't forget to give the video a thumbs up. Subscribe if you haven't already. You can also follow me on Instagram, TikTok, Math with Professor V. I'll be back sooner than later. Bye, guys.